Alright, one last thing from this section can be a little tricky when you get into the definition and all that. It does have a lot of value, especially as you get further into our precalculus here and eventually into the calculus, and it's called the intermediate value theorem. So we'll try to make this kind of short and sweet until we really need more of it. But for the time being, it means something like this. Let's say we have a graph of a polynomial function. So we've got our beautiful smooth curve here. And we're going to do a couple things here. We're going to pick a few points on our graph. So we're going to pick a point right here. And we're going to say that that's coming from point A. Well, every point has an x and a y. So in function notation, this would be coming from f of a. Now we're going to do another point here. And we'll say this one's up here at point B. So the x value is b, which means, of course, in function notation, its y value would be f of b. Now, one thing that's going to come out of all this, obviously we're stating that in this particular problem, a is less than b. Now, if that's the case, that means somewhere in the interval from a to b, the function, in this case we'll just call our function function f, that function takes on all values between f of a and f of b. So in other words, if I'm going between a and b, and I pick another value here, we'll call it c, as long as c is between a and b, then that means my function that I'm going to get over here, or my function notation f of c, also has to be between those two things. So basically, picture kind of shows that if I have something between a and b here, then between their outputs, I also have to have a solution. Now, what's the practical use of this? Well, some of the practical use would mean something more like this. Let's go back to a graph here. So let's go with this. So we've got an xy axis, and on that xy axis we have a picture, and on this one let's just make it something fairly simple. So let's say it's going to be one that's going to come up, slowly come back down, and then go back up. Not that the shape itself is real important. Now we're going to find 2 points on our graph, and we'll label them both. So let's go with our endpoint here, and let's say that's at -2, -3. And let's find another value, let's find another point here, and let's say that point is at -1, 1. Obviously not drawn to scale, but you get the idea. So basically, this is going to tell me that here we said between a and b there was some value c. Well, here we've got our x value of -2 and -1. So between that interval from -2 up to -1, that also means that I'm going to have a value between -3 and +1. Now, since this is negative and this is positive, as long as this is continuous for a polynomial, to go from negative to positive, somewhere I have to cross 0. So in other words, my intermediate value theorem is letting me say that if I'm going from a negative to a positive, somewhere between this interval between -2 and -1 is my 0 of this problem. Alright, so let's look at an example of this. Let's say we've got this equation. f of x equals x to the third. Again, that's technology at its best. X to the third minus x squared plus 1. Alright, now they might ask us to approximate the 0 using our intermediate value theorem. What are they actually asking us to do? Well, this is all they're asking us to do. Give us an x, and for every x, obviously we get an f of x. Alright, so right now it's going to be basically just some guess and check. Let's say we're going to start out with negative 2. If I put negative 2 in to the third power, I get negative 8 minus negative 2 squared is 4 plus 1, or negative 11. So negative 2 in gives me negative 11 out. All right, let's go to negative 1. If I put negative 1 into the third, I get negative 1. Negative 1 squared is 1, so we're subtracting 1 plus 1. And again, we're going to get negative 1. Let's put 0 in. So this and this are going away, and I just get 1. And if we put 1 in, 1 to the third is 1, minus 1 plus 1 is just 1. Now, the important parts of this one are this stretch right here. My y value changed from negative to positive. Well, between negative and positive is a 0. And it happened between my interval from negative 1 to 0. So what that tells me is, if I were to look at this on a number line, from negative 1 to 0 on my x-axis, somewhere in here is going to be my intercept. Now I can get as exact as I need to. I can narrow this down and go to the nearest tenth. So I could start at negative 1, which gave me negative 1, and I know I can go up to 0, which gave me 1. So somewhere between there, I could go by tenths. I could go at negative 0.9 for my x value, negative 0.8, negative 0.7, and so on, and get my corresponding output for each of those. And I could go as far as I wanted. I could go to nearest tenth, which I did here, nearest hundredth, nearest thousandth, and I could keep getting more and more specific until I find exactly where I'm going to cross there. So again, a lot of guess and check if you're using this method, but it's going to get you as close as you possibly can to where it crosses from negative to positive. And that's one of our uses for our intermediate value theorem.